This conference will now be recorded.
Hello, everyone. Welcome to the Vitrek webinar on work safety with high voltage and HIPOTS. My name is Don Milstein, president of Vitrek, and we're going to get everyone on the line as they're starting to come in, and we're right about at 10 o'clock West Coast time, 1 o'clock East Coast. So let's give it a minute or two, and we'll get going. Appreciate everyone joining the conference. We have a few other people joining in. We see our numbers continue to rise. A good turnout today for this webinar. And we're patient for another minute or two. We'll get going. Always fun getting these organized and people jumping on. All right, so why don't we get started? Again, good morning. My name is Don Milstein. I'm president of Vitrek. We'll also have Glenn Broderick, will be our main speaker today. He's our Western Regional Manager. And, again, welcome to the Working Safely with High Voltage and HIPOTS. We're excited to present this webinar. We've been doing that past couple of weeks, different webinars every week during this crazy epidemic time, and really appreciate everyone taking time out of their day to give us a moment to present, and hopefully you'll learn something along the way. So with that, on the next slide, you can see on this one has Glenn's number. We will make this presentation available to everyone after the session. It'll be mailed out. But obviously feel free to take notes as you go, but we will be mailing this out. Again, my name is Don Milstein. My contact information is there. I'm president. Glenn Broderick, Western Regional Manager, and his contact. Glenn, why don't you say good morning, everyone, so they can hear your voice?
Good morning, folks. Thank you for coming. I see you have a very good showing today, and I think we're going to have some good information for you. So,
So,
Don, did you?
Yeah, I'll get started. So, real quick, Glenn has well over 25 years experience in test and measurements. So I think you're going to enjoy his presentation. What we're going to do is we'll take periodic stops throughout the presentation, and at that point, You'll be able to chat throughout the session, so you can always at any time go to the chat button. Usually it's in the top right-hand corner, looks like a little bubble. Feel free, and we have people monitoring the chat to respond to you. At the same time, we'll highlight those chats at the stop area. We'll have everyone's phones on mute. If you're not on mute, that's helpful for background noise. But when we get to these sections, you can unmute your phone. And if you have questions, we can take questions that way. It's meant to be somewhat interactive. We've got a large group today, so makes a little bit of a challenge, but that's a good sign. So with that, let me kind of kick off, give you just a very quick intro, so you know where we're coming from with expertise in this area. Vitrek's been around for over 30 years in the industry. We're headquartered in San Diego, California. All of our engineering, production, customer service is handled there. So everything is American made in our facility there. And truly, even though we're in San Diego, we are an international company. We have over 30 reps in countries throughout the world, and we probably ship on an average year to 50 different countries. So we definitely take a global view to test and measurement, without a doubt. Our key product lines really historically have known for our HIPOT and electrical safety testers, along with cable testers for various types of cables. We have a full line of power analyzers for analysis and energy consumption review. A high voltage meter, really state of the art for calibration stations, for people doing testing and safety in the laboratory space, both at the private labs and commercial labs, as well as other high voltage testing. We have a line of DC loads, fairly new line out there for us, so something else you want to consider. And all of our products are, through our facility, are ISO 17025 accredited. So everything goes out, has that accreditation, and obviously we're set for in the future if you want to bring it back. But it's that 30 years of history that kind of helps with what we're going to be talking about and what we've seen as a company. And to the next slide. And again, this will be the slide that will show you if you have a question, and we'll stop, and you can, again, either unmute your phone or use the chat throughout. So please, feel free to ask those questions. And with that, I'm going to turn it over to Glenn. He'll be the main presenter for the rest, and I'll come back when it's time to ask any questions in the chat. So, all right. Thank you very much.
Don.
Yep, go right ahead, Glenn.
So this session is aimed to help you guys work more safely. When I'm out in the field working with customers, I quite often get asked, okay, we've got a HIPOT now, how do we use it safely? Because we understand it puts out some high voltages. It can put out 10,000 volts. And so, yes, it is, and you have to use it carefully. But it's not just people using HIPOTs that have to be very careful, because, in fact, most engineers, electrical engineers, and test engineers, and they're all working with high voltages pretty often. So what is a high voltage? Well, this standard here is taken from people working on power lines, and they tell you that high voltage is anything over 15,000 volts, and low voltage is under 600 volts. So my question to you is, what do you consider safe? Would you consider it safe to touch a 600 volt line? So when I was in the Navy, I was trained in the Navy, and they taught us on safety. And they taught us that anything over 30 volts could be considered a dangerous voltage, okay? Now, the way they did that was they ran tests, and they looked at how low the resistance of your body could be, and they took the absolute worst case scenarios. Now, a lot of people think 30 volts is too low, but I wanted to point out to you that EN 61010, it confirms this. It says the same thing. It says anything over 30 volts RMS or 60 volts DC can be dangerous. Okay? Now, here's a couple of guys just sitting around having fun, and they're looking 9-volt batteries. And believe it or not, 9 volts can hurt under the worst circumstances, which is your wet tongue. That's a pretty conductive environment. So you've probably been using dangerous voltages all along. The main goal is to avoid electricity through the heart and the brain. Everyone thinks of the heart, but the brain too, right? I mean, think of the electric chair. So there's an old myth that says electricity takes the path of least resistance. And that's not true. It takes every path available. So think about if you have a power outlet and you've got 6 sockets and each one has 115 volts on it. So just because one's driving a light bulb, which is a low resistance load, doesn't mean you're safe to touch the others. And the same thing goes for lightning. You can be standing out in the field and you can see lightning hit a tree. Well, okay, it's got a nice low resistance path, but that doesn't mean that you're safe. In fact, it can spread out, and anywhere there's a voltage, it can put a current through you. If there's a path, it will go through you. So, you know, the basics, everyone knows this about conductors and insulators, but maybe you didn't know everything. See the picture on the left, that's a big insulator, and that's used for the big power companies when you're talking about kilovolt voltages being transferred. Conductors are any material that allows electrons to flow. Okay, pretty obvious. These can be obvious things like silver, copper, gold, and aluminum, but you may not have realized that the periodic table, 2/3 of it are metals. So 2/3 of all the elements out there are a metal, and they conduct. Also, water, strangely enough, water is a really good insulator. In fact, I've worked on radar systems where we ran it right through the radar, and we used it to cool the radar. But the trick to that is you have to remove all the impurities in the water, because any minerals, any dust, anything like that can conduct, and turns water from an insulator into a really good conductor. Also, you may not think of it, but dust and gases can also conduct, and your human body can conduct. So the goal here is to make sure that doesn't happen. Now, insulators, they're the opposite. They have little or no conductive properties, and examples of those are glass, rubber, mica, and some plastics. But even if you have an insulator, it can break down. So an insulator that works at 1,000 volts might not work at 3,000 volts, as an example. And that's why we use HIPOTs to measure these things. Same thing for air. 15,000 volts per inch in dry air, it'll arc over, break down, and you'll have a big spark gap going on. So the nice thing is, if you have a HIPOT, you can measure if it's a conductor or an insulator, and you can prove it. Now, this is a chart of physiological effects of electricity through the heart. So it turns out that if you have, I'm just going to work with 60 hertz here. If you have a few tenths of a milliamp, you can feel it, of current going through you. At over a milliamp, it starts to hurt. And at 9 to 6 milliamps, I'm sorry, somewhere around 9 milliamps right here, it's painful. Okay. So your brain sends electrical signals to your muscles, and they tell them to move. Well, if you have another source of electrical signals, it can override the signal from your brain, and you will be unable to let go of wires. Okay. This can happen around 16 milliamps of current through the body. Okay. Severe breathing happens, difficulty breathing happens at around 23 milliamps. Now, the main thing to know is the lethal currents are typically on the order of 100 to 200 milliamps for 2 or 3 seconds. Those can cause heart fibrillation. So the goal is to not see that kind of current running through your body. But even if it's not going through your heart or your brain, if it's a high enough current, it can burn your tissues and your organs. Now, if you take a look at your body, you measure the resistance from hand to hand, finger to finger. It's typically about 1 megohm. Now, also, if your skin is wet, and especially if it's sweaty because it has minerals that can conduct, your skin resistance can drop down to 17 k ohms. So you want to stay dry. The other thing is cuts and jewelry can lower your skin resistance. So your skin acts like an insulator, just like an insulator around a wire. And if it's cut, then you conduct a lot better. Same thing for jewelry. It effectively creates many entry points for the current into your body. So those are things to avoid. So this is dangerous voltages and currents. Any current that's 100 and 200 milliamps for 2 seconds through the heart can be lethal. And again, that can happen with 30 volts if your hands are wet or you have cuts in your skin. Just under worst case scenarios, that can happen with 30 volts. But the most dangerous voltage of all is 115 volts. And that's because it's everywhere, and people are so used to it that they don't respect it. And I don't know if your mother ever told you this, don't stick a knife into a toaster. A lot of people have died that way. It's something you don't want to do. She was right. But you've probably been working with dangerous voltages all along, and you've never realized it. I can tell you I would rather be shocked by 3,000 volts from a HIPOT, one of our HIPOTs, than 115 volts from the wall. And the reason for that is the HIPOT puts out a low current, but the 115 from the wall has a breaker that's probably 10 or 20 amps. So it can put out a very high current. Now, I don't know if you know this story, but back in 1903, there was a big fight between Tesla and, this is Thomas Edison right here. Tesla had worked out all the theories for AC, and he wanted to electrify the United States with AC. And there's some advantages to AC, and he was right about that. But Edison said, no, AC is more dangerous, and I'll prove it to you. And so he went and he electrocuted this elephant right here. That's a picture of it being electrocuted in 1903. Now, we give these slides out to everyone who attends this session. And if you go to that slide and you click on that elephant, it's going to take you to Wikipedia. And on there, you'll find the write-up of this, including the movie. You can watch the elephant get electrocuted. And I have to tell you, it's really depressing, so I don't recommend it. But Edison was right. AC is more dangerous. It can be 4 to 5 times more dangerous than DC because it causes more severe muscular contractions. That means you can lock onto the circuit that's shocking you, and also it makes it easier to get the heart fibrillating and all that. Another reason is it stimulates sweating, which lowers the skin resistance. So the frequency of AC has a lot to do with the effect on the human body. And it turns out that 60 hertz is one of the most harmful frequencies. So obviously other frequencies are dangerous, but 60 hertz, the one we picked for all of our power, just happens to be one that has the most physiological effects on the human body. Now, capacitive coupling. So as an engineer, I'm sure you've seen this formula before. Reactive capacitance is equal to 1 over 2 pi Fc. And that means as this frequency goes up, this reactance goes down, and that means the resistance goes down. Effectively, the impedance goes down. So here's an example. If you take a 1 microfarad cap at 60 hertz, it's a 2700 ohm impedance. If you take a 1 microfarad cap at 1000 hertz, it drops from 2700 ohms to 160 ohms. That means more current through you. So as frequency goes up, you get more current, okay? So your insulator may not protect you from AC sources. So insulators typically measured at DC, but at AC frequencies, they can capacitively couple and still shock you. So as the impedance of insulation drops, your frequency, okay, we got that. Shock hazards increase, yep, capacitive circuits must be discharged after DC test. So for an example, when I used to work on radar, they had a high power transmitter. And so when you turned it off and you wanted to troubleshoot it, we had a big rod about 3 feet long, and we clipped it to ground, and it has a big resistor inside. And so what you do is you touch all the capacitive areas of the transmitter, and you discharge them so that you can work on it. So this has practical applications for what you're working on as well, because if you have capacitors that are charged up, and if you don't discharge them, even if the power's off, even if you think you're safe, you can still get shocked. So I put this in here. This is a pretty common chart. Everyone in engineering has seen it, but it's kind of handy if you want to figure out current. So current is equal to voltage over resistance, or power over voltage, or the square root of power over resistance. And you can use it, it's just kind of a handy chart as well. Any questions?
I don't see any chat questions at this point. Anybody have a question you want to ask verbally? You can just unmute your phone. All right. We'll keep going and
okay.
let Glenn continue as well.
So don't do this. These are things that you can easily do. For instance, I've been shocked by 8,000 volts, but I'm still here. I'm still talking. And the reason why, I was working on a radar traveling wave tube. It only put out 15 milliamps, just like a HIPOT. And so it didn't kill me, even 8,000 volts. Okay. But you've probably also been shocked by high voltage. You may not realize it, but when you walk across a carpet and you touch a piece of metal and you feel that shock, it takes 3,000 volts for you to actually feel it. And it can be up to 21,000 volts. So you've been shocked by 3,000 volts. One of the big things with ESD is below 3,000 volts, you don't feel it. So you can have a 500 volt shock that zaps your IC and destroys it, and you'll never even know that's happening. That's why you practice good ESD techniques. So even if it's not high voltage, high current can also burn you, okay? So you have to watch for that. We do ground bond tests with our HIPOTs up to 40 amps, and it's low voltage. It's maybe 5 volts or somewhere in that area. And so you want to be very careful that you don't get burned as well. Oh, and matter of fact, one time I was burned on a car battery. I thought, well, it's only 12 volts. I mean, you can look at a 9-volt battery. Why would a 12-volt battery hurt me? And I shorted it with a screwdriver, and the screwdriver heated up in a second or two, and it burned me pretty good. So just because it's low voltage doesn't mean it's safe either. Don't operate near water. We've already talked about why water can be a good conductor. Especially don't step in the water. That may seem obvious, but people have died that way. They'll touch on electrical circuits, they step in the water. Now, even low voltages, low current can still be dangerous. Now, here's some examples. When I was in the Navy, we worked on big racks of electronic equipment, and they told us a story of a guy who worked on the back of the rack. He had to stick his head in and put his arms in and reach back, and he was bolting something in. And he got a shock, and, just the surprise of it, he jumped back and he hung himself. So just because voltages are low, any kind of surprise can actually be dangerous in the workforce as well. So something just to watch for. So are HIPOTs safe, okay? Our HIPOTs, and here's a model, a 95X, okay? Typical maximum output is 50 milliamps. So you can see that's below the threshold of 100 to 200 that's typically lethal, okay? On the V7X in AC, 20 milliamps max, 10 milliamps DC. Now, you can also put current limits on the HIPOTs so that they don't even get to 50 milliamps. So, for instance, you can establish a failure if it hits 30 milliamps and then say stop on failure. And you can also buy them a 95X and you say, I don't want 30 milliamps, so we'll limit the current so you don't get that. So, our HIPOTs generally don't put out lethal currents. Also, a good HIPOT self-monitors and has multiple automatic safety trip shutoffs. And other testers may not do this, especially the old testers. In the old days, a HIPOT was just basically a step-up transformer. And it was connected to the wall, and it would put out a lot of current. So, and they didn't have a lot of safety. Matter of fact, probably no safety measures put on those things. So you may, sometimes I walk around factories and I'll see this big old HIPOT, from days past, and they can be quite a bit more dangerous. So how do you stop a HIPOT? Okay, well, this is part of a front panel of one of ours, and you have about 5 different ways you can stop it. One of which is press stop, that big red button, pretty easy to do. Okay, you also have a remote start-stop switch you may have enabled, and you can just hit that button. you can have an enclosure, and that enclosure can be interlocked. And so you basically just open the enclosure and it will shut off automatically. You can send a signal electronically via our digital input-output jack, and you can send a program command via things like Ethernet. So lots of different ways to stop it, but it will do it automatically too. It's watching itself, and it's pretty smart. So if the current on the high exceeds the limit, and that's assuming you've got the high safety setting, you have to turn it on, okay, which is the default. But if that's on and that high current gets too high, it's going to automatically shut down. Now, the return, it's important to have a return on these systems, and there's a continuity sense which must be enabled, which by default is, if someone pulls the black wire, not the hot wire, but the black wire, that return opens, it will shut the system down automatically. Same for if the high voltage is even different than expected. So let's assume that you're putting out 10 milliamps of current, well, let's say 30 milliamps of current, and only 10 milliamps is coming back. Well, it's kind of like a GFI. It kind of realizes there's something wrong, and the system shuts down automatically. Now, that's sensing external things, internal things. The microprocessor monitors the load and the performance, and if there's any unexpected behavior, it shuts down in 10 milliseconds. Now, remember, it takes 2 or 3 seconds usually to cause health problems, okay? Also, if the microprocessor itself starts acting erratically, okay, it shuts down in 100 milliseconds. Again, all safe things. Now, who uses HIPOTs? Well, you saw the picture of the elephant being electrocuted in 1903. People were using voltages and currents before that, and they were HIPOTing before that. And in fact, homes were burning down, buildings, businesses were burning down. And so the insurance companies decided they had to do something about it because they didn't like paying out the claims. So what they did was they worked to create organizations like UL and CSA and TUV and the standards for testing to make sure everything's safe. So using a HIPOT goes back a long time. They've been done for a long time. Engineers were HIPOTing circuits before oscilloscopes were invented. HIPOTs are used anywhere electrical or electronic products use insulated wires and components. If you see a factory like this, probably there's HIPOTs in there, checking everything that's going on. So that's, in addition to that, you should understand that HIPOTs are used to qualify designs. They're used for pre-compliance testing and compliance testing. So if you go to a test house like UL or CSA or TUV, they probably use HIPOTs in their testing. And so you can actually get your own HIPOTs and do your own testing in-house so that you know when you get to the test house it will pass. Production testing, usually the test is a little faster. Qualification tests are a lot of times 60 seconds. Production tests are a lot of times 1 second. But it's important to test every product to make sure it's been built correctly and that you have good insulation that's wired properly. That's especially important if the device has a metal chassis. So I have seen people HIPOT plastic vacuum cleaners because if you have a screw that's exposed and maybe that screw goes into the chassis, it's possible even though the whole chassis is plastic, you could touch the screw and get shocked. Okay? But if it's got a metal chassis, that's the big danger. So metal chassis devices are supposed to have a third wire on the power plug for ground, and it's important that that wire is hooked up and that it's sufficient gauge to handle the currents in case there's a big shock. Okay, so if there is a short inside a device like this, it goes to ground, and then the ground keeps it shunts that current off to earth ground. Okay, that's how it makes it safe. So HIPOTs, especially if they have ground bond capability, are really good for testing these things. So who else uses these? Any company that wants to meet legal and regulatory requirements, and companies that want to keep their employees safe, and companies that don't want to kill their customers, and companies that don't want to get sued. That's who uses HIPOT. So from a business perspective, you want a HIPOT because you may not be able to export unless you have these certifications. You may want, I'm sure you want higher quality and a safe product, and you want less lawsuits. Okay. So when working around high voltage, one of the things you want to do is set up a work area for safety. So obviously, make sure you have good earth grounds, that your power outlet itself has a good earth ground, and that your power cords all have all the wires, and that you've tested those power cords with a HIPOT. You want to ensure there's clearance around anything that's high voltage. And the reason for that is because high voltage can arc over. If you think, I used to think that you'd walk by a power line, and if you didn't get near it, you'd be safe. That's before I realized that capacitive coupling, it can arc over even if you're 3 or 4 feet away and can get you. So high voltages, it's a good idea to put up a barrier like this. You see this barrier right here. This small work area has been fenced off. And the other thing is, again, if you have any capacitance, make sure everything's discharged to a safe level when making any adjustments or touching any of the circuitry. Obviously, follow all manufacturer ratings and recommendations. Okay? So that's the first part of workstation safety. Here's some more things for you. Post safety signs. I kind of like this one on the left. I think it's graphic, and I think even if you don't speak English, it gives you a real good idea not to touch things in that area. You can use palm switches, a remote start switch. Basically, you can put a switch like this in. It goes to the back of that HIPOT, and the HIPOT won't start unless it sees this closed. So the intention is that if you put your hand there and you put this, 3-4 feet away from your device under test in your high voltages, then good chance you won't be able to get onto that high voltage circuit. Now, if you want to be even more safe, you can put 2 of these. And what that does is you put left hand on that one, right hand on that one, and now you know both hands are safe, okay? You can also put down a rubber mat. I like a rubber mat, especially if you have one of those ESD floors that are conductive. A rubber mat can be helpful. And something they taught me in the Navy, if you're near an energized circuit, put one hand in your pocket. If you don't have a pocket, put it behind your back. And the reason for that is that it's very hard to get a shock in through one hand and out the other if one hand is not available. Okay, so take off any conductive jewelry. Wedding rings. I was always taught you take off your wedding ring, and sometimes you have to explain that to your wife when you get home, but it can be worth it if it protects you. Okay. These are safety enclosures, and they're a good idea. So the way they work is the DUT goes inside the safety enclosure, and the tester and the operator stay outside. Okay. This is metal. It is conductive, and the reason why this makes you safer is because it's tied to ground, so that if anything happens inside to cause a high voltage to touch that metal, it is fully grounded. It'll probably blow your fuse, hopefully, but if not, you'll be at 0 voltages if you touch that. Okay? And you notice that little safety light on there. That's optional. You don't have to have it, but that can be wired up, so whenever there's high voltages on, that turns red. One thing about using enclosures like this, it's important to periodically test the ground on the enclosure and inspect the high voltage wiring going from the tester into the enclosure. So you want to look for cracks, or you want to look for oil or grease or anything that would cause the insulation to not be effective. Okay. Any questions?
Looks like we're good on the chat line. Anybody want to open up a mic for a question?
Hello.
Want to have a question?
Hello. Can you hear me?
Yes, we can hear you. Go ahead.
Okay, we use our Vitrek in the production area. And we did kind of a similar an enclosure is really nice, the idea. And we use a mat on the floor, so when the operator is on the mat, you have energy on the enclosure, and we put some safety switches. But one thing that I saw in your presentation is the having signs. I don't have that in the area, which
Well, that's a good idea. And you know, you can go online and probably find that sign and just print it out and put it up. It's not like you have to mail away or pay money for it.
and how to. I would try to implement a periodic maintenance to verify that that all the switches are working properly. That's something that we don't have.
How do you periodically test it? Is that what you're asking?
No, the enclosure to test the switches, because what we did is the doors on the closures are connected to the mat too. So if the door is
that's real easy to test. So the way you test it is you start the HIPOT up and you open the door, and then HIPOT should shut down. That's how you test the switch. It's really easy.
Yeah, but I want to implement something that more is working for us. We did something similar with the same 80/20 on plastic. We were able to find it.
Okay.
It's really nice.
Yeah. Now, regarding testing the ground, you can do that with a multimeter, but you also have a HIPOT, so you can HIPOT the ground. I like to do a ground bond. I'd like to put 30, 40 amps of current through it and make sure you have a good ground. I don't know if you know the difference between continuity test and ground bond, but continuity test is very small current. You just make sure that it's connected. But a ground bond puts high current, and it makes sure not only is it connected, but it's not going to melt through if it's actually needed. So it sounds like you have the tools to do all that.
Yeah, I will share it later. I will send you an email. I'm interested on the ground thing. Okay.
Okay. So I see a question: how frequently should you check the enclosures? And my question to you is, how safe do you want to be? There's no standard that I know of for it, and there's no recommended interval. But I think once a week would make sense, before you use it, maybe on Monday morning before you start testing. And I'm going to show you, go ahead.
I'm sorry, or maybe implement it with the same verification of the Vitrek that we do every day. Every day in the morning, we verify the Vitrek is working properly at the time.
Sure, sure, absolutely.
Not a bad idea.
Yep. Here's a question: where can we purchase these enclosures? We have them. Just ask us. We'll send you information on it, and we'll send you quotes for it. So, it's funny, but lots of people use HIPOTs. I bet the vast majority don't use enclosures. But I think if their management knew about the safety issues, I think they would. I think they'd all buy enclosures, the people that can afford that. So, and I think workers, if you're going to be working around high voltage, you might want to ask your management to get these for you. Any other questions? Okay. So, train for safety. You want to make sure anyone using the equipment is trained. I think just even going through these slides is a big part of it. Or, we're recording this. You can have your employees go watch this later. And to me, that's a good part of training people. You can read the manual. Matter of fact, there's a lot of safety ideas in the manual. Too many for me even to copy and paste and put into this presentation. So I definitely recommend anyone using the equipment read the manual. And the other thing is, if someone's not trained, you've got to block them out so they can't get near your equipment. And we'll talk about barriers in a second, but 10 feet is a good distance. This is a operator checklist, and I recommend printing this out and posting it somewhere in your work area. And it's a lot of the things we've talked about already, but it's just a good reminder. It's kind of like when you go to the pool and they got a list of things not to do when you go to the pool. it's a good idea to have some safety ideas up. By the way, it's a good idea to train people for CPR too. I don't know if you have a program for training CPR. So it's your duty, if you're using high voltage, to make sure other people stay safe. And the person most likely to be shocked are the ones that aren't aware of the situation. So that's why you need to keep them away. The other thing is watch for people who are impaired, okay? So, you need to say this in today's day and age. I know some alcoholics, and they can't go very long without drinking. Same for drugs. You shouldn't be running a HIPOT if you're impaired. And managers and supervisors need to watch that to make sure they're not near it. Okay? So there's another thing about safety, which is stay alert. Safety starts with you. And try to anticipate what can go wrong. And I'll give you an example of that. My sister owned a sign company up in Las Vegas. And it was a big sign company. They put up the big signs for the casino. And they had about 30 workers and 3 or 4 cranes. And one day this worker decided to go up and work on the sign, a loft. We call that a loft in the Navy. And so he went to the junction box. He opened it up. He pulled the wire off the high voltage, and then he climbed up the crane and started working on the sign, and he was electrocuted. Now, he did everything right, but in this case, he didn't know this, but the wire that he pulled off of the high voltage, it was a little bit springy, and when he was aloft, it just sprung back and got him. So I remember when OSHA came in and talked to my sister and said, hey, how come he didn't have any safety training? And her answer was, he was our foreman. He'd been doing this for 30 years. And he was the guy who safety trained everyone else. So safety starts with you. Try to be aware of what's happening. Anticipate what can go wrong. Anticipate if something can fall, be pulled down. If someone can be bumped into something, keep an eye out for those things. Now, in the Navy also, when we were on a ship and I took over the watch, okay, I'd walk up and I would be relieved, and we have a formal ceremony. And the guy who I'm relieving, he spends about 10 minutes telling me the status of the ship and what's going on, okay? Who's on watch, where are they at, which generators are online, which equipment's on, which equipment's red tagged out. And one of the key things we look for is what's different today, what's unusual today, because it's usually that gets you. You don't expect it because it's different. Okay. Now, part of being alert, when you run a HIPOT, usually, especially at higher voltages, you hear a buzzing sound. That's the transformer in there making the high voltage. So even if there's no lights on or anything else going on, if you hear a buzzing sound, be alert. This is a picture of the high voltage light on the HIPOT. When they put out high voltage, they light up red, and you see that nice little sign there. So if you see that on, be alert. And you've seen the safety light on the enclosure. I showed you that. So that's another thing to watch for. Now, there's a variety of government and other associations that put out standards that you should be aware of. And I think the NFPA, these are, I think, the most important. NFPA, the National Fire Protection Association, 70E is about protecting workers. And it has ideas in there. Probably a lot of what I've told you, but it wouldn't hurt to review that. NEC 2014, National Electrical Code, same thing. But OSHA has got a lot of good tools up on their website for safety training. In fact, they have an entire electrical safety training kit, which you can buy with like videos and DVDs and so forth. So these are all things that you can do. If you click this, you get the slides, you click on that, it takes you to OSHA, and there's a whole section on safety for your workers, and then the safety kit. So just remember that you can meet all the standards and someone can still get hurt. So they're the minimum, but you always have to keep aware of anything that can be unsafe and try to anticipate it. So that's really about all I have to say. I hope that is helpful and keeps you safe. And are there any questions?
Yep, please go ahead, open up your mics if you have a question. I don't see anything else on the chat. Good job there, Glenn. Looks like you covered a lot of material.
Hi.
Anybody have a question?
Could you share with us this presentation?
Yep, this will be emailed out to all attendees after the session, either later today or something like that.
I think it was helpful. We have 3 Vitreks from you guys, and we rotate them.
You know, we're also going to have this presentation on YouTube, and if you ever get any new employees and you want them to know about this,
do you have other presentations in YouTube from Vitrek? Or
we
do you
do.
have a channel?
Absolutely. What's that?
I mean, do you have a channel in YouTube?
Yes. Yes,
Nice.
we do. So you'll find there's a few videos like how to run a V95X and some of our other equipment, but we'll post this as well. And that means, you know, hopefully even years from now, you get a new employee, you'll remember them and point them.
Yeah, I need to train another guy too. Okay.
If you go to our website, on our website, you also see a library of these webinars that you can just click on. So whether it's YouTube or going directly to our library, you can see these and play them again. Any other questions? All right. Good job, Glenn. I want to thank everyone for attending, and obviously be safe in your properties and in your testing as well as in this pandemic. And no other questions? Glenn, thanks again. Any closing words?
Okay, guys. Happy testing.
Yep, right. You too. Thank you.
Appreciate everyone's time. Thank you.
Thank you.